So, okay, so here I showed you the reciprocity between the 2 points on the boundary. This is the most fundamental part of the reciprocity issue. Okay? So then, this is interesting, but since I'm from engineering school, to find, even numerically, to find a solution for point source is difficult. Okay? I want to consider more applicable form. I want to obtain a more applicable form. This is very interesting, but more applicable form I want to have. But it is, so then what I consider is the following. Here, these are the, say, green function. And this is a linearized system. Therefore, in some sense, you superpose this boundary effect, then you can construct the general solution. But my target is not construct the general solution, but just to obtain some simple relation between the two problems for the same domain. And this is some kind of result. So here, the key issue is that, so since we express the green functions for point sources by these notations, and GW, I'm badly organized the blackboard writing, but GW is PW plus 2 zeta I UI UWI plus zeta square minus 5 over 2 tau W. Okay? So therefore, the general solution for the same domain should be expressed by the sum of these guys. So like this. This is just a principle of superposition. Now, so then if what I want to consider is, so for general case, because the phi is expressed in this way, therefore you can calculate any flux by using this phi, especially, of course, any flux on the boundary. And from now, I would like to concentrate on the flux on the boundary at some point, for example, here. Okay? So then, if you, to obtain this, okay, so I use here, for example, the first component. First component is this one, okay? And the position is x0. This phi is expressed this way. So therefore you can just substitute this form into this definition. Into this definition, you obtain this form. This is just the substitution of this general form into the definition of each flux, each flow. This is a mass flux. This is a heat flux. This is a momentum flux. But you may say shear stress on the boundary at some point. Then here you have this component, okay? But this component, we learned that in this slide, we learned that these guys can be are the same as these guys. So by using this reciprocity, you can replace this part by using this one, in this way. So then we have a useful representation for each flux, mass flux, heat flux, and momentum flux on the boundary. It's too bright. Maybe how should I? I don't know how it is clear for you to see. Not effective. Yeah, it's good. Maybe better than before. Okay. So here, the point is that now I used this relation in the previous form. Then I obtained this expression. So here, if you are interested, say here, if you this guy is expressed on the terms of the first line. Okay? So please see here, the source term is common in these three forms. Before it was not. Before this source term, the type of the source term is different. But by using the reciprocity, now you have the expression by using the same source. Okay? So, for example, this line means what? This line, if you want to know the mass flux here, then if you want to know here, you just find a solution for the source point, mass source at this position. Okay? In general case, for you may consider arbitrary distribution of the temperature, arbitrarily moving boundary, arbitrarily distributed pressure. You may consider such general situation. And if you are interested in the mass flux here, then in place of solving the original problem, what you have to do is that you just put the mass source here and find the solution. Then, if you have this information, then you can obtain, because this is a mass flux induced by the point source at this point. The stress tensor caused by the mass point here. Heat flux caused by the mass source here. So the original general problem is reduced to finding a solution for the only one case. That the mass, if you you consider the problem with only the mass source here. In the same way, to obtain the heat flow, you are interested in the heat flux at this point. What you have to do is just to consider the problem for the temperature source here. This reduction is very much important when you reduce the problem because for to consider the general situation in numerics, you have to do a lot of things. But it tells you that what you have to do is just only solve one problem. Then, by using that solution, you can reconstruct the mass flow for arbitrarily distributed boundary data. Okay? Of course, this is still the point. To find the solution for point source is difficult, but in many cases in engineering, of course, you are interested in some one point, but usually most of the case, people are interested in the total heat flow, total heat that some body receives from the gas, for example. So the next stage is if you integrate this result for some part of the surface, then you obtain the total mass flux coming to this, passing through this surface. It is this result. So if you are interested in the mass flux that this S part receives, then what you have to solve is a problem. You distribute, what you have to do is just uniformly distribute the mass source here and find a solution of this problem. Then you can obtain mass flux passing through this point for any situation as far as the linearization is allowed. This part is heat flux. If you are interested in the heat flux passing through this surface, you have to solve only one problem, such that you heat uniformly here and find a solution for this situation. Then you can obtain heat flux for any situation. So my effort, if you are really interested in general situation for if you are interested in the solution for general situation, you have to obtain the green function for each sources and summer. So it does not mean any reduction of the problem. But here, if you don't mind the detail of the general situation, but instead, you are just interested in some mass flux, heat flux on the boundary surface. In that case, you have a chance to greatly reduce the problem, original problem. So this so the reciprocity is used for this purpose. Okay? So here I just make a phrase only shortly. So to know the flux through S, put the corresponding source uniformly there. That's all. Okay. So here I show you some simple examples. Consider the domain. The white part is a domain that the gas occupies. The grays are some body. Okay, body 1, 2, 3, 4, and 5. Say, so in some situation, engineer might be interested in the heat flux on body 1. Maybe, such situation may occur in general situation. Then in that case, in general situation means this boundary may move, the temperature distribution is any type. But in such situation, to know the heat flux on body 1, in general situations, it is enough to study only one case, that is, only this body is heated uniformly. The other guys are at rest, and the temperature, the same temperature as a reference state. Only this part is heated. Such situation, if you have information in such situation, you can get the heat flux that the body one receives in general situation. And the answer is here. So this part means the mass flow, momentum flow, heat flow that is induced when you uniformly heat body one only, and the other is the same as the reference state. If you have this information that in the heat flux on this body is just weighted sum of this elemental information. This is almost the same. Say for example, here you have two condensed phase, and between them you have a gas side. Condensed phase means say liquid. So if you have a CO2 gas here, you have a dry ice here. Such situation you may consider. Then, okay, so in this example we consider two cases. One is, okay, so we choose the reference state, we choose the state of this body as a reference state in this situation. Then consider just changing the state of this liquid slightly different from here, from this one. And the first case, case A, is you just change the saturation pressure. It is unphysical, but you can do it mathematically at least. So you just consider, just changing the saturation pressure. It is a case A. Case B, you just change the temperature here, and other parameters are the same as the reference state. If you consider these two situations, by substituting, by considering this representation, you find that heat flux that receives the outer interface for the case A. So only the pressure changes. In such case, the heat flux on this surface in this case is the same as the mass flux on this boundary for the case B, temperature difference. This is one example of Onzaga relation. Okay, up to this stage, I explained all the essential part of my talk. Okay, so what is the direction of generalization? Up to this moment, maybe I didn't explain it explicitly mention it. What I considered is only the case that the domain is bounded. Okay? And the boundary is a real physical one, not artificial boundary. Artificial means, say, so periodic boundary, or specular reflecting boundary. I want to include such case. And also, the other extension is the consideration of unbounded infinite domain. Because such extension gives me a much more interesting physical phenomenon. But the essence is already done. So maybe I just show you some result. Okay, I have 30 minutes, so maybe I can do that. So first is a finite domain. So considering the boundary other than the simple boundary interface such as the specular and periodic type condition. Okay. So this was the original version. Okay. We up to this moment we discussed this situation. Now I also want to consider some artificial boundary. So up to this moment, D is like this. And this boundary has a real physical meaning. Okay? So now I little bit extend this case such that some part, in some sense, some part of the boundary is not of this form. But I require very similar properties. And it is written here. So just change the notation in some sense. But the core part is that H is not necessarily of the form of G. And also K, the property of K is a little bit different from K. Original K. More intuitively, what I want to do is like this. I want to consider the channel flow. Here we have a boundary and channel, and if you give the pressure gradient, then the flow is induced. Such type of situation, I want to include this type of situation in my theory. Okay? So to do that, for example, the numerical people quite often do the simulation like this. You consider some square domain, and to represent the pressure, you use the, in some sense, periodic boundary condition here. But if you use the information, the information at this point to this point, it is not completely periodic. If you put a periodic condition, you cannot express the pressure gradient. Okay? So people do that. People subtract this guy. So except this part, people apply the periodic boundary. Such type of things people do to investigate the so-called power-wave flow, for example. Such type of things I want to include myself. Okay? So basic idea for the extension for the finite domains, behind my idea, this type of situation is included. The second case is, of course, say I want to consider some flow past a body. I want to discuss the reciprocity of this type of situation. I need a theory for unbounded domain. But I need one restriction, that the body is confined in a finite region. Because I need to use some asymptotic property at a far distance. Because of this reason, I need this the restriction of the body confinement. Okay? So my theory does not include. If you ask me, this reciprocity argument can be applied to this type of novel problem, my answer is no. I cannot do that. Maybe someone can do, but I. I don't say it's impossible, but at least it's beyond my ability, and very difficult problem it contains. Because in this case, at a far distance, even when you consider the Boltzmann equation, even when the gas is so rarefied, the molecules necessarily collide with others, because you can consider very, very long distance. So even when the mean free path is not negligible compared to this distance, but it can be negligible compared to the very far distance. Therefore, at a far distance, you can treat the gas flow by fluid dynamic rate. It is a key point. So in my case, the linearized Boltzmann equation corresponds to the Stokes equation for fluid mechanics. Then the far field property of the Stokes equation is well known, and I use this result. But for this case, even at a far distance, you have some layer here, and I cannot. I do not have any idea about how to treat this part. And as to this point, I consulted with Sone Sensei, but he said it is difficult. That's all. So I didn't consider further. Maybe you can do it. Okay, so this is a confinement. So I want to treat this type of problem. So here I show you more, say, detailed information, but as I told you, if I apply here the periodic type boundary condition, you can again show that very similar equality holds for this artificial boundary. It is almost the same as this one. And for this far distance case, because the far field can be estimated by the Stokes equation, and the decaying rate of the Stokes equation to the resting state, you can also show that this equality holds for this case. For this case, you first consider some control surface dg, and then you make the limit of r tends to infinity. So this dg means also including taking the limit of this one. So then what type of, so in this generalization, what type of relation you have? You do the same game as before. So this type of computation, you do it again. Then now, because of the new type of boundary, you have some additional term here. So this is essentially the same as before. So in place of dw, gw, I here dg and h. So this is essentially the same. And here, before, the cross term of GWA and GWB vanishes because of its special form. But here, this H is not necessarily of the same form as this one. So therefore, in general, it may remain. It doesn't vanish. So this is only different from the previous symmetric relation. But anyway, the symmetric relation, the role of A and B are symmetric again. Okay? Then, yeah, okay, so before we don't have this type of boundary, this type of boundary condition. We didn't have. So this part, for this problem, we had this original version representation. So now we have this type of part, this type of boundary. Then the result is that. Okay, so here and here the same, and here you have new term. Sorry. This one is this one. You have new term here. So this is a contribution of the new boundary, new type of boundary. But besides it, it is the same. And okay, wait. Sorry, what is? Okay, sorry. So this representation is for the point on the physical surface. But if you consider the point on the artificial surface, you have a little bit different form. It is this one. You have one more additional term here. But essentially, the things are the same. So for here, again, you have this term. Yes. This is the same as before for finite domain case. But for the flux at the far distance, we do not put the point source. Instead, we will consider the mass, momentum, and heat flux passing to this control surface, four control surface here. By the way, the Boltzmann equation satisfies the mass, momentum, and energy conservation. By using this one, you can replace this flux at a far distance, changes to the flux on all the surface of the body. So this is useful, especially when you are interested in the force acting on the bodies, the group of the bodies. Especially when this body is only one body, it means that you can compute the force acting on a body. So in that sense, this conservation law is very convenient for the engineering purpose. So this is a result. So the mass flux, heat flux, and the force acting on this surface can be obtained in this way. By the way, this notation means what? This notation means the state at a far distance is the mass of 1. This means the temperature of only the temperature is different from the reference state at a far distance. This is the case of the velocity. This is the mass. So then, maybe some examples. Maybe for this case, it is better to show the examples of this result. Here is the example that is intensively studied in our group. It is called summer pump, Knudsen pump. It is usually the vacuum pump having a mechanical system to evacuate the air in some chamber. But this pump has no mechanical part, but just by using the temperature effect, it has a pumping system. It is because in this example, I explained that if we have a pressure gradient, flow is induced. But for rarefied gas, if you have a channel, and along this channel, if you have a temperature gradient, in this direction, for example, the flow is induced in this direction. This is a phenomenon peculiar to rarefied gas. You do not observe this phenomenon in usual circumstance, usual fluid dynamics. You cannot explain this phenomenon. This is called the thermal transpiration. And this pump make use of this phenomenon. Here we have a thin pipe and a thick pipe. Okay? Combination of thin pipe, thick pipe. It is a cascade system. And along this thin pipe, it has a temperature distribution like this. And this part, temperature distribution like this. And in total, it has this saw type periodic temperature distribution. Then what happens? Because of this temperature, this means the temperature gradient from left to right. So in this part, this thermal transpiration occurs from left to right. But this part, because the temperature is opposite, temperature rating is opposite, the flow is induced from right to left. But because of the difference of the pipe radius, this thin part becomes dominant. And in total, the flow is induced from left to right. So in this way, you can evacuate, you can transport the gas from left to right. So if you have chamber here, you can evacuate from the chamber. Okay? This is a Knudsen pump. So what yes, so what if we apply our result to this system, what we can say? Yeah, this is a general representation in this situation. And okay, so this part, okay, maybe it's better to cheat. So this part is 0. Why? Because wait. どうしようかな。Just a moment. We are interested in mass flux. So therefore, yes, okay. So in this original problem, this dg is the artificial part. It is a part here and here. Because I explained, as you explained, here this pipe cross section, I use the periodic boundary condition. Okay? So this part corresponds to this part. Okay? And H is the boundary data put in here, but it is 0 in my case. So therefore this term doesn't appear, and this part doesn't appear, because H is 0. Because in this problem, for the periodic boundary condition, H is 0. And GW, PU tau is considered along this side, okay? Along this side, I only change the temperature, okay? So, and P and U is 0. So, therefore, to know this quantity, what we need is just this term. Then this, so therefore, now we are interested in the Knudsen pump. It means the flow induced by the temperature effect. So we are mainly interested in the mass flow here now. So to know this component through this part, what we need to know is just to this guy. So this guy means this guy is the solution of this problem when you put the point source here. So this is a relation. So therefore, to know the thermal flow effect, thermal transpiration, the Knudsen pump effect, for any temperature distribution, what you know is what you have to consider is the flow conductance problem of this one unit. Okay? You put the mass source, uniformly mass source here, then you solve this problem. And when you solve this problem, you know the heat flux passing through this surface for this conductance problem. Then you obtain the mass flow for any case, for any temperature distribution case. This is one example. The same you can say the same thing for the other type of thermal pump. Okay. Here, this pump is interesting. In place of changing the geometry, you have a straight pipe, but inside you have two arrays of plate. One is the same as the pipe temperature. The other is, say, heated or cooled uniformly. Even in such case, the flow is induced. It is verified numerically and also experimentally. My colleague Sugimoto-san, he is doing a lot of experiment of this device, and he has a patent from in Taiwan and also maybe also in Korea, I guess. I'm not quite sure, but he loves this experiment very much. And for this case, by the same argument, again, to know how much mass flow, how much flow you obtain by this device. To know that, what you have to do is just to consider the conductance problem. You put the pressure source at one end and solve this problem. Then you can obtain arbitrary, you can obtain the mass flux. So maybe this, yeah, maybe there are two containing involving this. There are two examples. So the next one is we call it Goltz's theorem. Professor Goltz proved this fact. Before I explained the Knudsen compressor, it has a thin part, thick part. Thin part, thick part, and because of the thermal transpiration, you have a one-way flow from left to right. But if you have a thin part and a thick part, if you don't have thin part, thick part, just the size is the same. You have just a straight pipe, and you give the temperature, periodic temperature. One may ask whether or not you can induce a flow from in one direction. His answer is no. He proved it mathematically for the linearized case. And I can reach the same conclusion as him by using my result. Okay? So, yes, here. So it's a little bit complicated, but if you formulate this problem, then yes, then yeah, okay. So if we apply our reciprocity result to this one, the mass flow passing through this cross section is given by this one. This is the same as before. Okay, 2 slides before I showed that this one is given by the heat flow induced by the conductance problem. So now this conductance problem is what kind of problem? If we formulate this problem, it is a solution of this boundary value problem. Then you can find the solution of this problem in this form. I don't need this similarity solution, but for simplicity, for simple explanation, I use this one. Then, by using this result here, okay, x1, yes, so phi, okay, so the point is that here Qn is, yeah, okay, here. Qn is zeta n times this one, okay? And now this one is expressed by this one and this one, okay? In this case, Qn is a component normal to the side wall, okay? Zeta 1 is axial direction. So therefore, this guy is this guy is even in zeta 1. This guy is even in zeta n. So therefore, by integration, this doesn't give any contribution. So therefore, this guy is 0. So the point is that by using the reciprocity, I change the original problem into the conductance problem. Then use the property of the solution of the conductance problem. Then I showed this, the vanishing of this mass here. Just some time. So maybe skip this. Okay. So there is one example, but I think I talked enough. Thank you very much for your kind attention.